Hello students, and welcome back to our class on improper integrals. In today's lecture I'll discuss the problems that I had given you as homeworks in the earlier lecture, and some of you have already done those and there were some doubts, so let me clear all of those in this particular lecture. So this was one of the problems. For what values of m and n does the integral 0 to pi by 2 sine to the power mx by x to the power nx x to the power n dx converges? Okay, so here we can see that the integral is of the form sine x by x. Okay, sine of something, sine to the power something by x to the power something. Okay, so there is an hint that we need to use sine x by x somewhere because that limit exists. Okay, so here we write sine f of x as sine to the power mx by x to the power n, which can be written as 1 by x to the power n minus m into sine x by x to the power m. Okay, so this part, the limiting value is 1, right? And so the convergence, or say the infinite discontinuity of the function, is determined only by this part. Okay, because as x tends to 0 plus, sine x by x always tends to 1. Okay, so the problem will be created for infinite discontinuity. The problem will be created only by this part. Okay, so for n minus m, so if this is n minus m is negative, okay, then the integral is proper. Okay, so a negative or 0. Okay, so the integral is improper if and only if n minus m is strictly greater than 0. Okay, if 0 is in the denominator, okay, in that case it will be improper, right? So it is proper for n minus m less than or n less than or equal to m, or n minus m less than or equal to 0. Okay, so for n greater than m, 0 is the only point of infinite discontinuity of f, and so we take gx as 1 by x to the power n minus m. So here it's quite easy or obvious choice for gx, because how do we choose gx? We choose gx in such a way that the limit fx by gx should be finite. Okay, so here is one hint that if I choose gx as 1 by x to the power n minus m, in that case their ratio will be just sine x by x to the power m, which always exists, and so we will get a finite limit there. Okay, so once we get a finite limit, we can conclude that the integrals converge or diverge together. Okay, this is the best way to deal with convergence. Okay, so limit x tends to 0 plus fx by gx is sine x by x whole to the power m, which is equal to 1 for all m. No matter what is the value of m, it's always 1. And since this is non-zero, so these two integrals converge or diverge together, right? But what we know is 0 to pi by 2 gx dx, that is 0 to pi by 2 dx by x to the power n minus m, converges if and only if n minus m is strictly less than 1, that is n is strictly less than m plus 1. Okay, so the given integral also converges if and only if. Okay, because of this limiting form of the comparison test, we can use the term if and only if. Okay, the first form doesn't give us this if and only if condition. Okay, so this integral converges if and only if n is strictly less than m plus 1. So this also includes the case n less than or equal to m when the integral is proper. Okay, so this is the problem. Another problem, this I did not give you probably as a homework. So let us do this. For what values of m and n is the integral 0 to 1 x to the power m minus 1 into 1 minus x to the power n minus 1 log x dx. Okay, so in the earlier lecture we have done up to this part the beta function that we had studied, the convergence, divergence. Okay, and so today it's this multiplied with log x. Let us see how the things change here. So here also we have to be very careful in deciding under what conditions the integral is proper, under what condition it's improper. Okay, because already we have a log x term here, so it's going to make some differences. So here 0 and 1 are the only possible points of infinite discontinuity. However, we have to have a closer look. So since log x is negative, so first thing, so this in the earlier lecture also I had done this type of thing. And yeah, one of you asked why we are considering minus log x. Okay, we need to understand that the convergence of 0 to 1 or a to b fx dx is same as convergence of a to b k times fx dx, where k is a constant. That means multiplication by constant is not going to change your convergence or divergence. Okay, so that's why we are free to do that. And for comparison test we need the functions to be positive, otherwise we cannot apply comparison test. So that is why we have to make the integrand positive. So here, how to make it positive, we will consider minus log x. Okay, so it's log of 1 by x, and since 0 and 1 are the points of discontinuity, so we split the integral into two parts. Let I1 equal to this and I2 equal to this. Okay, so here one common mistake that students mostly make is that they write let, or we have 0 to 1 this is equal to this plus this. Okay, so avoid writing that, because once these two are, both of these are convergent, only then we can write that the given integral is the sum of these two. Okay, otherwise we cannot write. So you do it this way, let I1 equal to this integral and I2 equal to this integral, and then we study the convergence of I1 and I2 separately. So convergence of I1 at 0. So for m greater than m minus 1 greater than 0, we have this limit x to the power m minus 1 log m1 minus x dx, or 1 by x dx is what? Limit of this is what? Log of 1 by x divided by x to the power 1 minus m. Okay, so this is of the form infinity by infinity, and we can apply L'Hopital's rule. So we will be left with limit x tends to 0 plus minus of x to the power m minus 1 by 1 minus m. Since m minus 1 is positive, so this integral is this limit is 0. Okay, so hence the integral is proper for m minus 1 greater than 0. Okay, for m minus 1 positive, the integral is proper. Okay, so yeah, so this part is there. So that means x, this log of 1 by x is not creating trouble. Okay, as long as m minus 1 is greater than 0, right? So we may think that yeah, there is always a point of discontinuity at 0. That is not the case. Okay, if m minus 1 is greater than 0, in fact, in that case the integral is proper. Okay, so the 0 is a point of discontinuity when m minus 1 is strictly is less than or equal to 0. So let m minus 1 less than or equal to 0, that means m is less than or equal to 1, or 1 minus m is greater than or equal to 0. So fx is this. Okay, so it's a quite complicated integral, and here the choice of gx is not that obvious or straightforward, just like the previous one. Okay, so we start with, say, gx equal to 1 by x to the power p. Okay, we will choose p later. Okay, depending on the situation that arises. So fx by gx is what? X to the power p plus m minus 1 into this into log of 1 by x. Okay, so just now we have seen, if log 1 by x is multiplied with x to the power something which is x to the power some positive power, in that case the integral converges, right? Yeah, the integral is proper. So we choose this, and for this term we don't have to worry. 1 minus x to the power n minus 1, when x tends to 0, it just goes to 1. So for this term we don't have to worry, we just have to worry about this two, log 1 by x and x to the power p plus m minus 1. Okay, so we choose p in such a way that this quantity is greater than 0. Okay, so so why we are doing that, I had already told in the earlier lecture, because we want the ratio limit x tends to 0 fx by gx to be a finite quantity, or to exist. Okay, and just now we have seen, if x to the power some positive quantity is multiplied with log of 1 by x, the limit comes out to be 0. Okay, which is a finite existing quantity. So we can go for our comparison test. So we choose p such that p plus m minus 1 is greater than 0, that is p is greater than 1 minus m, but already 1 minus m is greater than or equal to 0, right? This is already there. So we have limit x tends to 0 plus fx by gx is this. Yeah, so here again you can just see what I have done. I have just separated this into two product of two different limits. Why? Because both the limits exists. Okay, and so, and by L'Hopital's rule here we can find out it's 0 because p plus m minus 1 is strictly greater than 0, right? So we have got a finite quantity, but it's equal to 0. Okay, if it were non-zero, in that case the integrals converge or diverge together, but here I cannot put the same conclusion. Okay, here I can draw the conclusion only when this integral, the denominator integral or the comparison integral is convergent. Okay, if it is convergent, then the given integral will be convergent. If it is divergent, we cannot say anything. Okay, so the conclusion can be drawn if this is convergent, which is so if p is less than 1. So gx was 1 by x to the power p, so that is convergent when p is less than 1. So that means this given integral is convergent if so we already have 1 minus m is less than p by our choice of p, right? By our choice of p, 1 minus m is already less than p. Okay, and so this integral converges if 1 minus m less than p less than 1. Okay, that is m is greater than 0. So whenever m is greater than 0, 1 minus m is less than 1, and we can always choose a p which lies between 1 minus m and 1, and then the result of comparison test holds. Okay, so now the convergence of I2 at 1. So this is also something similar. So here also we will observe, but there is some differences here also. Is proper for n minus 1 greater than or equal to 0. That is obvious, we can see for n minus 1 greater than or equal to 0, this integral is proper because log 1 by x here is not creating any problem, right? When x tends to 1, log of 1 by x is just 0, right? So it's proper for n minus 1 greater than or equal to 0. That is obvious. Okay, but we have something more here. What is that? You will see for 0 less than or equal to n less than 1, we have limit of this quantity. Limit of this quantity is minus of limit of this, which is also of the form 0 by 0, and this can be written as 1 by x into, so ultimately the limit will be limit x tends to 1 minus x to the power n by x. Okay, but what is this when x tends to 1 minus? It's 0. Okay, so that means even if n minus 1 is even if n minus 1 is less than 0, okay, right, less than or equal to 0, then also there are some possibilities here. Okay, so if n lies between 0 and 1, even then the integral is proper because the limiting value is finite. Okay, so the integral is proper for n greater than or equal to 0. Okay, for n greater than or equal to 1 it was obvious. Okay, and for n greater than or equal to 0 we have proved it by the L'Hopital's rule. Okay, so that means we have to study the convergence only for n less than 0. N is strictly less than 0. So we proceed in the similar way, that fx equal to x to the power m minus 1 into 1 minus x to the power n minus 1 log of 1 by x dx. And since we do not know the choice of gx, so let us take it as 1 by x to the 1 minus x to the power p. Okay, so fx by gx is this, and just now we have seen that this part, this product, it evaluates to 0 or tends to 0 when p plus n this is greater than or equal to 0. Okay, not only when p plus n minus 1 greater than or equal to 0, its limit is 0 even when p plus n is greater than or equal to 0. Okay, so we choose p such that p plus n is greater than or equal to 0. Okay, so our limit will be existing. Limit x tends to 1 minus fx by gx will be limit of this, and we can separate and apply L'Hopital's just like the previous one, and you will see this is 0. So conclusion can be drawn if integration half to 1 gx dx converges, but which is so if p is less than 1. Okay, so therefore the given integral half to 1 converges if, so already we have p is greater than or equal to minus n, and for convergence we have to choose p is less than 1. That means our n should be greater than minus 1. So for n greater than minus 1, the other integral, the I2, converges. Okay, so hence this will converge if we have m greater than 0 and n greater than minus 1. Okay, so sorry, it's minus 1. Okay, if we have n greater than minus 1. So if this happens, then this is convergent. Okay, for other values we are not sure as of now. Okay, So but we are unable to do anything in this semester. Okay, so up to this you keep the problem. So yeah, one of you were having difficulty with this problem, but it's quite simple, it's not that difficult. Integration 0 to 1 x to the power n dx by 1 plus x. So here 0 is the only point of infinite discontinuity if n is less than 0. If n greater than or equal to 0, then it's always always a proper integral. So for n less than 0, the only point of infinite discontinuity is 0. So what is the choice for gx? It's very obvious. Gx is, you take gx as x to the power n, okay, or which can be written as 1 by x to the power minus n. Okay, so our limit fx by gx will be 1, which is non-zero. That means 0 to 1 x to the power n by 1 plus x dx, and 0 to 1 dx by x to the power minus n converge or diverge together. Okay, so it's always preferable to use the second form of comparison test. Okay, so try to avoid the first form, because the first form doesn't give you this if and only if condition. The second form is much better. Okay, and it's easier to do. Okay, so you compare this to take the ratio, choose gx in such a way that fx by gx tends to a finite limit. Okay, so here it's there, so they converge or diverge together, but this converges if and only if minus n is less than 1. That means n is greater than minus 1. So the given integral converges if and only if n is greater than minus 1. Okay, so it converges when n is greater than minus 1. Okay, next yeah, you were also having problem with this particular problem, this 0 to pi root x by sin x dx. Okay, so here 0 and pi are the only points of infinite discontinuity, because at x equal to 0 this denominator becomes 0, at x equal to pi also this denominator becomes 0. Okay, so what we do, we split this integral into two parts. One is I1 equal to 0 to pi by 2 root x by sin x dx, and another is I2 equal to pi by 2 to pi root x by sin x dx. So convergence of I1 at 0. So that's quite simple. We just choose gx equal to 1 by root x, because we have this sin x by thing, sin x by x thing in our mind. Okay, sin x by x, the limit will be 1. So you take gx equal to 1 by root x. So limit fx by gx is 1. So which is non-zero. So these two integrals converge or diverge together, but this integral converges because half is less than 1. So this part converges. Okay, so one part converges, the other part convergence of I2 at pi. Okay, so for pi I need to take the limit x tends to pi. So we have sin x here, but I can write it like sin of pi minus x. So what is in our mind? We are trying to convert it to the form sin of pi minus x by pi minus x. Okay, so we choose gx as 1 by pi minus x. So in that case fx by gx will be root x into pi minus x divided by sin of pi minus x, which can be written as root x divided by sin of pi minus x by pi minus x. But when x tends to pi minus, this this quantity tends to 1. So it's ultimately root pi by 1, that is root pi, which is non-zero. That means these two integral converge or diverge together. But what about this integral pi by 2 to pi dx by pi minus x? This integral diverges because the power here is 1. So this pi by 2 to pi also diverges. So since one of the parts diverges, so the original integral has to diverge, it cannot converge. Okay, so the answer given in the book was correct only. Yeah, so you can do it this way. Another homework which I had given was x to the power 0 to 1 x to the power m minus 1 e to the power minus x dx. Okay, so here also you can see it's obvious that the integral is proper when m minus 1 is greater than or equal to 0. So let m minus 1 less than 0 and there is m less than 1, then 0 is the only point of infinite discontinuity. So we take, so here also it's quite obvious. What is gx? Gx should be x to the power m minus 1. Pretty simple, because if you take this gx as this quantities will get cancelled and you will be left with e to the power minus x here, and its limit is 1. Okay, so this limit is 1, which is non-zero. So these two integrals converge or diverge together, and but we already know that this converges if and only if 1 minus m is strictly less than 1, that is m less than 0. So the given integral converges if and only if m is greater than 0. Okay, so I give you two more problems which you can try. The first one is a very famous integral which you had done in higher secondary. It's I think minus pi by 2 log 2, it evaluates to this, and It's a very common problem. It was asked in my higher secondary final exam also, I still remember. Okay, so it's quite simple, but the convergence part is new for you. Okay, we had just evaluated without caring about convergence, right? So you try to show that it converges, and you also try to evaluate it. Okay, it's there in the book also, but I would request you not to see the book first try to do it yourself. Okay, and another exercise, you try to do this and try to evaluate its value. It should come log 2 minus 1. Okay, so please try to do it. In the next lecture we will start with convergence at infinity. Okay, so if the limits are infinite, in that case how to deal with the convergence, right? So till then, thank you.